Hello everyone and welcome back. Now, in the previous video, I introduced you to the method of extended dynamic mode decomposition, EDMD, for approximating the action of the Koopman operator on a finite collection of observable functions. This finite collection of observable functions we termed a dictionary, and it's user prescribed. It's a hyperparameter of the method. But what we saw in the previous video is that EDMD can be very powerful for understanding and interpreting dynamical systems through the eigenvectors and eigenvalues of the Koopman operator. In particular, EDMD allows you to do this in the absence of governing equations. It allows you to get information about the system directly at the level of the data. Now, EDMD is a very powerful method that has been extended and applied to a number of different problems throughout the physical sciences. But it has some shortcomings. Let me, in this video, try and elucidate some of those shortcomings while also showing you how you can overcome them. And where I want to start is by thinking about this user-prescribed dictionary, okay? So when we have this user-prescribed dictionary, a lot of the time, one might use, say, polynomials or monomials up to a fixed degree. So that would mean that your parameter, your value k, which was this cardinality, the size of your dictionary, which I'll call d, this thing would be a function of both the size of the space that you're working on, which I'll call capital M, and the degree of the polynomials you're going up to. In fact, if you use all monomials up to a fixed degree d, this size of this thing turns out to be m plus d, choose d, minus 1. Now, you might be asking yourself, first of all, where does the minus 1 come from? It comes from the fact that you are never going to use the constant polynomial functions because they are useless in the interpretation of the Koopman operator. So if we disregard that, though, this can get very bad very quickly, right? Because we know that this thing is made up of factorials. So it's going to get very ugly. You can use Stirling's approximation to sort of figure out how this thing scales approximately, as m or d gets large. But let's just go, I've got some concrete numbers for you just to see how bad this can actually be, okay? If you go back to the very first application of dynamic mode decomposition that I gave you, the nonlinear Schrodinger equation, I discretized space into 64 different points. That means that my M would be 64. M-dimensional space, that's 64 spatial locations that I'm interested in. If I use even just degree 2 polynomials for EDMD, I'm looking at about 2,000 dictionary elements. K is equal to about 2,000, okay? If I go up to degree 3, I'm looking around 47, almost 48,000 dictionary elements. That thing's getting very big very quickly. If I went to degree 4, we are talking 814,000. Now, that is a huge dictionary. And I want to remind you that when you are doing DMD, you are computing this matrix A, which in the case of EDMD looks like this. Psi of y times the pseudo inverse of psi of x. Now, both of these matrices are going to be k by n, where n is your amount of data. In this case, this is n by k because the pseudo inverse is going to flip the dimensions. This is a k by k matrix as well. Now think about my last example. K was 814,000. That's an enormous, enormous matrix. If you try to do a pseudo-inverse computation, say in MATLAB or in SciPy or NumPy, with one of the dimensions being 814, you will probably crash your laptop. It is enormous, right? It's not going to work. So even though EDMD in this case works in theory, it does not work in practice. So what we are going to talk about today is a kernelized version of dynamic mode decomposition, kernel DMD, that takes advantage of the kernel trick from machine learning, right? This is coming from primarily support vector machines, where people notice that you can do this trade-off of dimensions to get information about a high-dimensional space using sort of low-dimensional computations. And in the case of kernel DMD, the way that we're going to do this is we're going to trade computations in size k for computations in size n, the amount of data. Now, if you think about how this would happen in practice, typically, maybe you have like 1,000 or 2,000 data points, for example, right? So that would be way smaller than my maybe 814,000 dictionary elements. So that means that if I can trade off all of these k by k matrices to make them n by n matrices and do some computations there, doing, say, eigenvalues and eigenvectors of a 2,000 by 2,000 matrix isn't nearly as bad as 814,000 by 814,000. So the question is, how can we do this? Well, we are going to have to introduce two assumptions. The first assumption is that our matrix phi of x, we're going to assume we have the SVD. Okay? Now, even if we don't have it in practice, we could at least we know that it exists, right? It's proven to exist for all matrices, so let's assume that we have it here now. And let's assume that we have a left eigenvector of the matrix A, right? So remember, whenever you're doing the Koopman operator stuff from the previous video, what we were really interested in was eigenvalues and eigenfunctions. So those eigenfunctions came from left eigenvalues of the DMD matrix. So that's what we're going to assume we have. Now, for the SVD, I'm actually going to assume further. Remember, this is a k by n matrix. And this is n by n. Now, I'm going to assume that I'm working with a reduced SVD, where U is going to be a k by n matrix as well, and sigma will also be an n by n matrix. Remember, k is assumed to be much larger than n, so this is a reduced SVD, but essentially it's just eliminating rows and columns that are all 0 from sigma here. Okay, now here's what I'm going to do. I'm going to set a new vector w hat times u star is equal to w. Okay? You can always just get this by inverting, but the important part here is that this is a k-dimensional vector. This is only an n-dimensional vector. Now, why is this helpful? Well, if I multiply both sides of this thing by mu, the eigenvalue, here's what I get. Mu w hat u star is equal to mu w. But also mu w is equal to w times a, by definition of the eigenvalue, right? But also w, again, if I go backwards, is w hat u star, right? And a is equal to this thing right here. So psi of y, psi of x, pseudo-inverse. Okay? Now, I can isolate this expression for u star. So here's what I would get. W hat. And then I get sigma pseudo-inverse v star psi of x. And then I still have a psi of y in here. And then what I have, I can do the same thing here. I can take a pseudo-inverse. And so now I get a v sigma pseudo-inverse u star. Okay. So did that help me? I mean, it's a really big, ugly matrix here. But take a look. I have a u star and a u star hanging out on both ends. And that means that if I define this big, ugly matrix right here, if I call this a hat, right? Now, notice that a hat is an n by n matrix now. You can do all your dimension counting. It's an n by n matrix. It's way smaller, 1,000 by 1,000 or something like that. then this eigenvalue, mu, right? So maybe I should just write it. Mu times w hat is equal to w hat times a hat. It tells us that these two matrices have the same eigenvalues as long as mu is non-zero. Similarly, the eigenvectors lie in one-to-one correspondence with each other for these non-zero eigenvalues. Okay? And the important piece here is a hat's way smaller, right? Computing eigenvalues and eigenvectors of this thing is way easier than computing eigenvalues and eigenvectors of that thing. Okay, so now our interest is identifying each of the matrices that make this thing up and see how we can put this back together. The first thing I'm going to do is I'm going to identify sigma and v, and this can be done fairly easily. In fact, sigma and v come from the definition of the SVD, and we saw previously that they can be computed like this. Here I have a transpose or a Hermitian adjoint. In this case, the real valued matrix, it doesn't make a difference if you use transpose or adjoint here. And if I do this multiplication, symmetric matrix is diagonalizable. And from the SVD, we actually know that this is true. Remember, we saw this back whenever we first learned the SVD, right? This is how we motivated the fact that every matrix even has an SVD. But what I really want you to notice here is that this is an n by n matrix, right? And so since it's an n by n matrix, computing its eigenvalues and eigenvectors should be pretty simple, potentially, right? 2000 by 2000 or whatever it happens to be. It's in terms of the amount of data instead of the size of the library. So that means that 1, 2, 3, 4 matrices can be computed in theory from very low dimensional pieces. The only thing that remains is this matrix product and this matrix product. And again, these two things on the inside have hidden dimensions of k. That's where all the high dimensionality is contained. And the way that they're multiplied together right now, they come together and annihilate the high dimensionality and leave me only with the relatively low dimensionality. So the real question here is there a way of computing these matrices that can not kill my computer, right? And the answer is very much yes. This is where the idea of kernel DMD comes from, and kernelization. So let's take a look at this. What I want to do is I want to figure out what the entries of this matrix actually look like, okay? So let's do, psi of x, Hermitian adjoint or transpose, whatever you prefer, psi of x, the ijth coordinate of this matrix. Well, okay, we're going to use two things. We're going to use the definition of matrix multiplication, which is dot products along rows and columns of the matrices. And also, you'll have to recall what these things actually were from the previous video, right? So I'm going to write it out. This is psi 1 of xi, and then all the way up to psi k. So every single dictionary element at the same column of x, which represents the snapshots, dotted with the same thing happening over here. xi dotted with xk. Sorry, this is xj now, pardon me. xj, like this. And that just comes from the fact that I have a transpose here, but really this is just every dictionary element at one point in time dotted with every dictionary element at a different point in time. And really, the way you can think about this is, if you'll allow me a little bit of shorthand notation, psi, without the sub-indices, maybe as a vectorized notation of xi, let's use transpose instead of adjoint here, just to emphasize it's real, psi of xj. And here I'm just doing this as a vector notation. Psi just means the whole vector of this thing. There's no sub-index. But it's just going to allow me to get away with, a little bit of easier writing of things down. And so what the kernel trick aims to do is find a function that evaluates to this product. Okay, so how do you do that? Let's take a look. Let's do a little example here. Okay? Before I move on, I want to talk, I want to give a specific example so you can see exactly what's happening. Let's look at the case of m is equal to 2, a two-dimensional system. And let's look at this function, h of x, y. Each of these things is a two-dimensional object, right? So each one is in R2. And it's going to look like this. 1 plus x dotted with y to the power of d. Okay? Now, let's just look at a specific example of d equal to 2. In this case, d is going to represent the polynomial degree. I'll show you where the correspondence comes from in a second. It's fitting exactly into this. But if d is equal to 2, let's just look at what happens here, right? 1 plus x dotted with y squared. Let's just write it all out. 1 plus x1, y1 plus x2, y2 squared. And then if you write this whole thing out, you get 1 plus, now 2x1, y1 plus 2x2, y2. And then you have all of these cross terms. So plus 2x1, y1, x2, y2. And then plus the cross terms right here as well. So plus x1 squared, y1 squared, plus x2 squared, y2 squared. Maybe I didn't explain that properly, but I mean, it's just expanding out this polynomial. Now, actually, you can recognize this as a dot product in this form. In fact, in this case, my vector psi of x, like in this formulation, looks like this. 1 square root of 2x1 square root of 2x2, and then x1 squared, x1, x2, and x2 squared. That's a vector of functions of x. And you can see that this thing right here, when I take a dot product with itself, so h of xy is equal to psi of x dotted with psi of y, which is the same as just multiplying transposes, right? So I'm kind of switching around with notation here, in part just to kind of keep you on your toes and make sure that you really are sort of fluent with all these different notations. Once you start getting into data science, notation becomes inconsistent a little bit because mathematicians have their own way of doing things, statisticians, computer scientists, physicists, so it's good to sort of see this mix, even though you might be thinking that I'm just doing it to mess with you. But essentially, that means that through the function evaluation h, I can compute these dot products if I am using a dictionary of monomials up to degree 2. Now, in fact, this holds for any m and any d, right? This function will compute all of these dot products that are composed inside of these matrices in order to produce a basis, a dictionary of monomials in m variables up to degree d. So I'm going to leave that for you to check for other degrees. But here's the basic premise. Now all you need to do is you can recognize that this thing right here, if you were looking for degrees up to degree d, for example, for monomials, that would just be, let's actually just write it. Psi of x, adjoint or transpose psi of x, ij is equal to h of xi comma xj. Now take a look at this. If I have the h, assuming I have a polynomial dictionary, I never have to actually compute these matrices. All I have to do is function evaluations, which requires a dot product. A dot product is just pointwise multiplication and then summing it all up. That's n plus 1 operations. Very, very easy, or maybe 2n operations if you want, or 2m operations, pardon me. But this also allows you to work with other bases as well, because I can introduce other functions h that can implicitly define these matrices without me ever having to look at them, right? I don't actually need to know what my dictionary is. All I need to know is what my function h is, okay? So, for example, sometimes people use other choices of h. Sometimes you'll find people use things like the Gaussian. There's a very, very common example of function that people use, especially this is getting you very close to the theory of reproducing kernel Hilbert spaces. And so Gaussian kernels there are very important. And in this case, you want something like x minus y in the Euclidean norm squared, and then you have some sort of normalizing factor sigma. Or you could do, or h of xy is equal to, sometimes people just use this x minus y. This is sometimes called the Laplace kernel, and you can also introduce a normalizing factor in there. So no square, that's the only difference. Or the one that we just saw above, which is the polynomial kernel, this, x dotted with y to the power of d. And as we saw with this one, we can explicitly compute what our dictionary is going to be. It's just going to be all polynomials up to degree d. But with these ones, it's not clear exactly what the dictionary looks like. But again, that doesn't matter, right? Because here we have all of the entries of this matrix just by doing these evaluations. That means that I can find this matrix and I can compute the eigenvalues and eigenvectors to put them into this. Similarly, this guy right here, psi of x star times psi of y, you can look at the pairwise entries here. It becomes basically the same thing. You just swap an x and a y out. And in this case, you are just going to get h of xi yj. So again, you don't actually need to compute these matrices. You just put them into this sort of universal function, which we call a kernel k. And so now, this is very good for us because this gets us a lot closer to getting eigenvalues and eigenvectors out of this original DMD matrix. Because I can compute this just by evaluations in H. I can compute this by evaluations in H. This whole thing now is done as n by n matrix multiplication, way smaller. There's no hidden dimension anymore. The hidden dimension comes from the kernel trick. And so that means that I can compute eigenvalues and eigenvectors. And so the question is, how do I get Koopman eigenvalues and eigenvectors back? Right? This is the most important part. So Koopman eigenfunctions. Well, here's what I have. Remember, by definition, a Koopman eigenfunction looks like this. W times psi of little x. And here I'm just using the same notation you saw down here. Psi is representing this whole vector, and this is just sort of a dot product, all right? So W, remember, was the eigenvector, the left eigenvector of the DMD matrix A, okay? But now, let's do a little bit of simplification here. W was assumed to be W hat U transpose, or U star, whichever you would like to use. Again, let's use star to be consistent. I'm kind of jumping around. And then times psi of x, right? So that's just the definition here, dotted here. Now, psi U star, we already did this manipulation right here. I get W hat sigma pseudo inverse. And then I get a V star or V transpose, right? It's just this thing. And then I also got a psi of x pseudo-inverse. Or sorry, not pseudo-inverse, Hermitian transpose. And this is all multiplied by the vector psi of x. But in fact, this multiplication right here is the same as this multiplication, just with this thing being a variable, right? So that means that this really is w hat sigma pseudo-inverse, which I have, v star, which I have, and now this whole thing becomes h, and then at each data point, x1, comma, x, a variable, h of x2, comma, x, all the way down to h of xn, comma, x. This is a vector valued function. It comes from your kernel function. The first piece of it is evaluated at each of the data points. The second piece of it is the variable. This is genuinely a function of x, and it does not require me to explicitly compute out what each one of these dictionary elements actually is. Again, this is the kernel trick. This is an n-dimensional vector. It's very, very simple. Sometimes you call these things the features if you're talking about reproducing kernel Hilbert spaces. But the beauty here is that everything is done in terms of the dimension of the amount of data you have, which hopefully, if you're going to use this technique, is way smaller than the size of the dictionary that you wanted to use originally. Let's take a look at an example. And I'm going to apply kernel dynamic mode decomposition to synthetic data from numerical simulation of the Burger's equation. Now the Burger's equation takes the form u sub t, so that the partial derivative with respect to time is equal to a parameter nu, which we call the viscosity parameter, times a diffusion term, right? The second derivative in space is a one-dimensional partial differential equation, 1D in x, plus u ux. So you have this sort of nonlinear drifting term. So here's how I'm going to do this, all right? Let's take a look. Here I'm going to fix my viscosity parameter to be 0.1. Just this is going to sort of slow down the decay. If the viscosity parameter is larger, this thing decays to 0 very, very quickly. So I just want to see something interesting in the dynamics. I'm going to time step it according to a time stepper of 0.01. I'm going to time step up to time 10. And then my spatial domain is going to be from minus pi to pi with periodic boundary conditions. And let's this is the initialization here. I'm going to run 5 different random initial conditions here. So I'm going to probe the system with 5 different initializations, let it run, and that's going to be the data that I collect from this thing. If we take a look here, our USOL, can we see this very well? So this is going to be on a grid of 256 spatial points. That's way more than we used for the nonlinear Schrodinger equation, right? So trying to use EDMD on this, it's going to fail. Even at degree 2, it's going to be a brutal problem. So let's take a look at what maybe a solution might look like. Let's run this section. Just a moment. Here we go. So here in red is the initial condition. In blue is what happens after time 10. You can see a nice little wiggly superposition of signs here. And then if we interrogate this, you can see it very, very sort of quickly peters out and decays down to 0. Okay, there's a little bit of a drift that happens. You can see this from the top, just a little tiny bit, and that's coming from this nonlinear drifting term. But nonetheless, let's use a dictionary of polynomials up to degree 2 with that polynomial kernel function. So that was the 1 plus x dot y to the power of d. So that d is going to be degree 2. Here's the matrices that would otherwise in DMD be very, very large. Here, watch how quickly this will go for us. It ran before I even finished speaking, right? That was a very, very quick computation of what would otherwise be very, very large dictionaries. Here I'm going to do the SVD. I'm going to use a reduced rank SVD because there's going to be a whole bunch of zeros in this thing. And now I can actually just plot the eigenvalues and eigenvectors of my A hat matrix. So in this case, sorry, just the eigenvalues, but let's take a look. Here's what my eigenvalues look like. So most of them are inside the unit circle. It doesn't have a whole lot of meaning unless you actually sort of dig into what a Koopman representation of this matrix or of this PDE should look like, which has been done in the literature. I'll link to it in the description. It was done in part by Jacob Page, I believe with his advisor, Kurzweil. But let's take a look. Let's just sort of compare what happens if I increase the degree, right? Because if I increase the degree of the problem, standard EDMD is going to make my DMD matrix even bigger and even slower to compute. But take a look at this. Almost nothing here really depends on, you know, the degree increasing. It's just an exponent. It's not going to slow down the computations at all. So if I run this, already finished. If I run this, here's my eigenvalues now. You can see them starting to collapse onto the positive real axis. In fact, this is what was proven. The true eigenvalues of the Koopman representation of this thing should all lie on the positive real axis. So if you can compare mentally with what you saw previously, you can see this convergence happening. Let's increase again. And 1, 2, 3, very, very quick. Again, you can kind of see this convergence happening, especially up near the eigenvalue 1, which for a DMD matrix, the eigenvalue 1 for discrete time is very, very important because that's the one that doesn't either blow up or decay as time goes on. And let's just do one more application here, degree 8. Again, look how long this takes. You don't even notice it run, right? It's immediate, whereas this would be an enormous problem. And here you can kind of see these eigenvalues. They're forming this sort of beautiful little pattern here, but you can again see them starting to collapse at a non-uniform rate along the along the real axis. Now the point here is that computations are quick. And that's because everything is in the amount of time. So if we look at the length of our time vector, it's only 101 units per initial condition. There's 5 initial conditions. We're talking about 505 time steps that we're looking at here, okay? That means that, you know, we're computing eigenvalues of 505 by 505 matrices. That's quick, that's cheap, that's easy to do, right? Compare that with all of the degree 8 polynomials in, let's take a look here, 256 variables. I don't even know what that number is. I suspect that if you put that into the formula from the very beginning of this lecture, you'll probably blow up your calculator, right? You probably need, it's probably bigger than, I don't know, maybe a Google or something like that. Let me know in the comments if you actually did it. But until then, I'll see you all in the next video, everybody.